When it comes to connections to the terrestrial Earth, there is perhaps no orbital regime that is more important than that of the geosynchronous orbit. And thus, if you really want to have mastery of RPO, it is incredibly important to understand how this orbit works and even have an intuitive or instinctual understanding of motion and distances at this orbit. So that's kind of what this lesson is designed to do. It's built around the GEO Rules of Thumb or GEO Approximations of Thumb, just some very basic rules that you can know and memorize that will allow you to make some conclusions about motion in this particular orbital regime. Okay, jumping in with the first rule of thumb, the first one that we're going to cover is that the orbital period of a geosynchronous satellite is approximately 24 hours. That is exactly what it means to be a geosynchronous. So you can see this geosat will always be over Greenwich, England, or the west coast of Africa. Because it is traveling in its orbit once per rev at the same rate of the Earth, which is also 24 hours. Now you might be thinking, big deal, how does that actually help me with making decisions in an RPO space at GEO? Well, this rule of thumb, despite its simplicity, is actually incredibly useful for building that instinctual understanding. Okay, so let's use our first application of this rule of thumb. So I have two RPO satellites. One is RPO satellite 1, which is moving in this large NMC, and the other is RPO satellite 2, which is moving in this drifting NMC. Both are starting at the same location, and both want to arrive at this point on the geosynchronous belt. So the question is, which one is going to get there first? And indeed, how much faster will one reach the location versus the other? Using our first rule of thumb, that the orbital period is 24 hours, it's incredibly easy for us to know the answer to this. You have to remember that every orbital period has some distinct features, and one of the easiest and most distinct features that we can tell just from this visual space here are apogee and perigee. So every orbital period has one point of apogee, the distance furthest from the Earth, and one point of perigee, the distance closest to the Earth. So you can see that RPO satellite 2, which is in this drifting NMC, is currently as close to the Earth as it will ever be, meaning it is its point of perigee. And then you just go and you try to find the next point of perigee, which is here. Since there's only one point of perigee every 24 hours, meaning the periodic motion of this satellite, we know that from this point to this point is 24 hours. RPO satellite 1, which is in this large NMC, is currently not at apogee or perigee. You can see here is its point of apogee, and here's its point of perigee. So from here, this point of apogee to perigee, that's 12 hours. To do one full rotation, one periodic motion, is going to be 24 hours. So from here to here, I'm halfway through my orbital period, which means it's only been 12 hours. So indeed, as we click through the hours, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. In fact, RPO satellite 1 has already reached that location, whereas RPO satellite 2 is only halfway through its orbital trajectory. And now you can see 12 hours later, RPO satellite 2 finally arrives, whereas RPO satellite 1 has returned and completed its full orbital period. Okay, here's another application. Two satellites, both of them are at apogee. Which one will reach this location first? Well, you can see RPO satellite 3 is moving to this perigee point here, and it's 12 hours away from this point. RPO satellite 2, which is the same from before, is currently at its apogee, and it's moving to this perigee point here. So it's also 12 hours from this point, which means that RPO satellite 3 will get to here in 12 hours, so it gets to here in 6 hours. In 6 hours, RPO satellite 2 will not yet be at its perigee. Despite the fact that it looks like it's much closer, it's actually going to get there 6 hours later, and let's just watch it. Here's 6 hours. As you can see, our RPO satellite 3 beat it there. And RPO satellite 2 is still going to be another 6 hours before it actually reaches this location. There it is, RPO satellite 2 is now here, and RPO satellite 3 is at its point of perigee. Okay, here's another classic example. So periodic motion is not just radial in-track motion, but it also covers cross-track motion. So here we have RPO satellite 4, which has an inclination difference from GeoSat, and it's on this typical hourglass shape that you see with inclined orbits. So, okay, how long for RPO satellite to go from here to here? Its northernmost point. Well, if you just trace out the motion, you know that all motion at this orbital regime will have an orbital period of 24 hours. So for RPO satellite to move up to here, from here to here, and then back is halfway through its period, because you can see you have another leg that you have to go. So from here to the top is going to be 6 hours, back down is going to be another 6 hours, to here is 6 hours, and to here is 6 hours, because it has to be able to complete this loop in 24 hours. And there you see it, 24 hours have elapsed. Watch one more time. 1, 2, 3, 4, 5, 6. It's at its point highest. Another 6. It's descending through the equatorial plane. Another 6 at its southernmost point. And then another 6, it's ascending through the equatorial plane. This is true if you have drifting motion as well. Although the drift will change the orbital period slightly, within about 1,000 kilometers of GEO, you can still pretty much make all of the same conclusions. So here you can see this snaking, sort of sinusoidal wave-looking formation for the RPO sat. So we know that this point, the northernmost point, peak will happen once every 24 hours because of the periodicity of the motion. So the distances between these peaks, 1, 2, 3, that's 3 days, because each one of these will be 24 hours apart, just like these troughs or southernmost points will be 24 hours apart. So let's see. Let's go to that first one. It's at 0600 on the 2nd of August. Now let's see where we're at 0600 on the 3rd of August. Okay, and then you can see we've moved 24 hours, which we've just jumped to the other peak. And then let's see where we're at the 4th of August. Yeah. Each motion that you see in the RIC frame, if it returns to the same apparent point in its periodic motion, that means that one full period has elapsed, e.g. 24 hours have elapsed. So that's how you can use this GEO rule of thumb to describe both RI and C and very quickly make conclusions. So if I see the shape, I know that it's going to be 24 hours to reach GeoSat. I don't have to check the Keplerian elements. I don't have to run any reports. I don't have to push play and wait 24 hours. I just know this is periodic motion, and it will take 24 hours to reach this point. It'll be here in 12 hours, here in 6 hours, etc. Powerful, instinctual. One final thing that you can think about with the first rule of thumb that is very easy to take advantage of is the fact that because this orbital period is 24 hours and the day-night cycle of Earth and really satellites that follow the surface of the Earth is also 24 hours, if you're in an NMC and you have a particular sun angle to a portion of the GeoBelt, then this sunsat, which is in an NMC around GeoSat with the sun directly at its back, will always have the sun directly at its back. So we can just watch this happen. So you can watch the sun is tracking around GeoSat. At the same time, sunsat is tracking around GeoSat as well. So the sun vector will always point to sunsat. Something that we might call a sun-phased NMC. Okay, so moving on to rule of thumb number 2. The second rule of thumb that I want to talk to you guys about is that 1 degree at the geosynchronous altitude is 736 kilometers wide. Okay, so how can I possibly use that? Well, the great thing about GEO is because your satellite is apparently non-moving with respect to the Earth, it's very convenient to describe orbital location for a satellite based on its longitudinal location over the Earth. So here you can see GeoSat is longitudinally over the prime meridian or the 0 longitudinal point. RPO satellite 1 over here is 1 degree east of GeoSat. And it's very, very common to describe the location of satellites or a location of space at GEO according to the longitude of the ascending node or the longitude of that particular orbital regime. And since we do that quite commonly, it's good to just have a fundamental understanding of how wide those distances are. If you think of the United Nations and the ITU slots that they afford satellites, which I think are around 2 degrees wide, that's just saying that your satellite is afforded approximately 1,500 kilometers of space that it can live and exist in. And if you have a satellite that is 1 degree away, it is 736 kilometers away from you. Just builds that sense of scale to make informed decisions. So if someone says you have a satellite that's 2 degrees away, you don't need to get a calculator or draw some vectors or anything like that. You can just say, oh, okay, it's about 1,500 kilometers away. So you can see it, RPO satellite 1 is 736 kilometers away. If I move RPO satellite to 2 degrees longitudinally, you'll see that it is now double that distance, which is 1472. So one other thing you can do with this rule of thumb is just realize how vast space is. So if you think that these are only 2 degrees away, and there's 360 degrees at GEO, and each of these satellites might be the size of a passenger car. Imagine a passenger car in a space that is 1,500 kilometers wide. It's very, very empty out there. Okay, guys, so that's just 2 quick rules of thumb that allow you to have a sense of scale and a sense of time when it comes to objects and motion at GEO. In the next video, I'm just going to cover some approximations or rules of thumb that we use to very, very quickly calculate maneuvers that will allow you to move in this free space. So check that video out if you want to learn how do I use in-track radial and cross-track burns to change my orbital parameters and produce the motion that I want at GEO.